Class, we talk about the transform and the Fourier series. Here shows the homework 7 already we have done. Firstly, we would like to find out the impulse response of these systems. It means that if we apply xt, the output becomes xt minus 3. Then if we try to delta as an input, then output should be delta t minus 3. We know that if input is impulse, then the output is the impulse response. That's why they are given like that. If we have impulse response, then we can take a transform like this forms. I already talked about where does it come from. So the index should be goes to minus infinity to infinity, and taking the integration of delta function, it has only non-zero value at t equal 3. So we just replace t is a 3, then this integration is done. So we got this result. This is the first question. The second one, if input is applied sinusoidal function like that, we can decompose that one as a complex exponential function like that. So we know that each response of that. Firstly, if this input is applied, then output will be this is just the input scaled by this transform functions. You know what? S is replaced by J4. So if you replace the S with J4, it gives minus 12J from here. Then we can have this result. Similarly, we can try for it minus J4T, and it gives this one, and J7T, it gives it J7T minus 3, minus 7T, J minus 7T, J is omitted here. So by combining all these things, we know that this one is a superposition theory. Then we can have this result. The next one we talk about the Fourier series. To understand the Fourier series, we try to find out the fundamental period and frequency like that, and this is given. We can expand periodic signal as a linear combination of complex exponential. So that's these equations. So from this linear combination of complex exponential, we would like to figure out the complex coefficient Cn. So at here, if we replace xt with this summation, then we can write down it that way. But in these cases, these exponential terms have non-zero value if k equals to n. Only non-zero value at k equals to n. So k should have n. In that case, this is Cn, this goes to 1, and taking integration over the period. So actually this one is Cn times t0, but at this moment t0 is 1. So that's why this gives Cn. So this means that Cn. And another point of view, we can replace xt with this graph. Then during this 0 to the 0.5 period, xt is 1. So we can just calculate this one. And then it gives this result. We need to interpret n. N equals the even number. Then 1 minus 1 goes to the 0. But n is odd number. This becomes the minus 1. That's why it gives 1 over j and pi. So this is the odd cases. Try to find out the an and bn. In these cases, we can expand xt within these equations. At here, a0 is just the same as c0 because n equals to 0, the e to the j minus j n omega 0 harmonic component is 1. Similarly, cosine n omega 0 t, if n is 0, then this is also 1. So that gives us the average of the signals. So we taking integration over one period, then this gives the C0 or the same as A0. So n equals 0 is a special case, except that we can express the Cn and Bn like that. If n is even, then it's 0. So in that case, An and Bn is 0. So that's why in case of n is even, Bn is 0, an is always 0. So if n is odd, then we can using this result at here. So by use of that one, plus n and minus n, it gives actually these terms are remain, but this term means 0. So an is 0 and bn are equals to 2 over n pi by comparing the coefficient of cosine and sine. So we got the result. It says that the an is always 0, but bn is 0 even, n is even, but n is odd, then bn has some value. an bn can be directly calculated by use of these integrations. So it says the same result. an is always 0, but bn has a 0 in case of n is even, but n is odd. This one is similar, so I just briefly explained. We would like to find the C0 first. The C0 is just taking average of them one. xt is non-zero value between 0 and 0.25, so it gives us 0.25. And Cn, except n is not equal to 0, we can try these equations. Then we got this result. In this cases, e to the minus j 2 pi of 2 is minus j, so it gives like that. We need to interpret n. N can be separated as 4 different segments. We need to consider this n is n has a n divided by 4 remainder is 0. In that case, it's 0. So it taking n equals 4, 1 minus 1 goes to 0. In case of remainder of the division is 1, then we can try n equals to 1. In that case, 1 plus j. If remainder of the n divided 4 is equals to, we can try n equals 2. In that case, minus j square I equals minus 1. So it is 2. So 2 and 2 cancelled out. Then j n pi is 1 over j n pi is the result. And finally, if n divided 4 has a remainder is 3, then we can try the 3. In that case, the plus j comes out. So we can have this result. Calculation is better. So we can take integration over the non-zero period. Then you can have this result. T can be taken 0.5 and 0. It gives this result. So an is cosine coefficient. You can try the same things. N is n as division remainder is 0. Then you can try 4. In that case, this goes to the 0. And you can try, in this case, you have this result and all the way down. And in case of Bn, you can has the result and interpret n in each case, then you can have this result. Before close out this homeworks, I would like to give some more idea what is the Fourier series. So I would like to use Excel plot. Okay. Fundamental frequency is 1 over T0. This has a unit Hertz. Omega 0. The omega 0 is 2 pi. Okay. Omega 0 is 2 pi f. It's omega 0. Unit is radian per sec. Okay. This is it. And to plot this one, we need to define the sampling times. Sampling, I would like to 1 over 20 times each period. This is sampling time. Sampling frequency is just the inverse of that. Okay, this is sampling frequency. And I would like to write down the times over here. Time starting from minus 1 sec. And time increasing by the sampling time, make it constant. Okay, so I can copy to up to maybe 2 seconds will be enough. So I would like to finish out up to here. Okay, 71 index. Okay, I would like to plot minus 1 to the 2 second. It means that minus 1 to the 2 second. I would like to do that. And xt is in this period, you know, the 1, so 1, 1, 5. Okay. 1. Okay, and from here I would like to shift down to 0. 0, 0, 0, 0, 0, 0, 0, 0. Okay, this is actually t equals 0. So at here, again 1, so it should be repeated like that. It's a periodic function. So another period and another period. And finally it should be 1. Okay, then I would like to plot that one. Then I can plot that things from here. Data selection starting from this, that's the xt, and end of 71, and this one also end of 71. Okay, I plotted this curve over here. It's a period from here to here is 1 second. It's a rectangular pulse. So what I would like to do is to, so the harmony index is n. Okay, harmony index is n, means that it's a frequency component. The first one is 0. That's the DC component. You can see that here are an and cn is just the integration, the whole period of xt. That's the average value of xt. Okay. Then this has only non-zero value between 0 and 0.5, and that magnitude is 1. So this is 0.5. So 0 cases, n equals 0 case. 0 harmonic, it's a DC component. DC component is 0.5. So I can write down DC component 0.5. Okay, all the way 0.5, and that's the 0.5. DC component 0.5, and n equals 1, 2. There is no even component. 1, 3, 5, 7, 9. Okay, up to 9. The magnitude of sine coefficient is the 2 over n pi. Okay, 2 over pi. So I can do that one for 2 over n divided by pi. Okay, this is it. That will be stretched over here. So it's a component is decreasing. DC harmonic component is 0.5, fundamental is 0.6, third harmonic is 0.2, fifth harmonic 0.1, seventh harmonic is smaller and much smaller. The even harmonic component all the way 0. So this one is a first harmonic. Okay, let's notate that first harmonic, and this one is x3. It means that it contains a DC and first harmonic. Then to express that one plus, I need to consider the first harmonic component. First harmonic component has only sine component because cosine component is 0. But sine component has this times sine. Okay, this times sine. Harmonic index is 1 times omega 0, and omega 0 times t. T is at this moment is this is t. So to stretch out that one, first this one is okay, previous one d9. You know that this coefficient. So 9th number should be constant, and d8 is this index. This index, harmonic index, also should be constant. B3 is constant, so I have to take a constant. B3 is omega 0, and time index, the A column should be fixed up. So I make it constant some indexes, and the same. The result is this one, and the stretching. Okay, this is x5t. x7t, x9t. You need to think about why I fixed these numbers to make it stretching like that. And then downward stretching. Then we can calculate all the way down. We added the DC and first harmonic components over here. Third harmonic, okay, DC, first and third are added here. and another added here. You know that it's accumulated. E11 is this one, and added the next harmonic component, added the next harmonic, add the next harmonic. So X9 means that the ninth harmonic component are added. So I would like to overplot the result from here. So data selections, I would like to select the up to first harmonic, okay, and the time changing from here up to 71, and the y-axis now I would like to plot first harmonic. Okay, then it looks like this one. From here you can compare the original rectangular pulse and the first harmonic component are estimated like that. Okay. What about the one more harmonic component added? So to do that, I can add. At this moment, I would like to plot DC first and third harmonic component added it together, and X changing similarly 71. This is time axis, and third harmonic this one 71. Then that's this gray number. Okay, sorry. Yeah, third harmonic. This is time axis. This is harmonic index up to 3. Okay. Here shows the DC plus first and second harmonic are given this gray graph. So if you add up its harmonic component, then what's gonna happen? I would like to plot the ninth harmonic. Okay. Okay. At this moment, if we add up the DC first, third, fifth, seventh, and ninth harmonic are added all together, that will be okay, much closer to the, okay, I would like to compare only XT and the ninth harmonic. You can see the orange curve shows that when we add DC first to the ninth harmonic component are added together, then it looks like the rectangular pulse. So if you're adding more harmonic component, more closely related each other, it's just you can see that the expansion converging to the rectangular pulse if you add up these coefficients. You know that this 2 over n pi sine is this value. Then what's the meaning of this value? This means that the DC first harmonic, third harmonic, fifth harmonic, seventh, and ninth harmonic each other. So we can plot this one. Then what's the meaning of that? Okay, let's plot that one first. To plot that one, I would like to insert plot over here, and I would like to plot with spectrum. We call that a spectrum. X change at this moment is a harmonic frequency, and Y value is a harmonic frequency component, amount of harmonic frequency component. Okay, this is it. And from here, I would like to add, okay, and okay, I do not need okay. Okay, I would like to close out. Okay, I only this part, and okay, and here I would like to unseen this axis. Okay, okay, this I would like to plot the spectrum graph. So to do that, I can try to use this one, and it's 100%. Okay, that is 100%, and I need to take only negative part and the color, and it will be about 2, and okay, and I'd like to replace the marker. Okay, marker, taking triangular. Okay, I plotted this one. I want to let you know that the meaning of this one. We call this one the spectrum. You can see this graph shows that the okay. Here. Okay, this one, and another one is this graph. Okay, look at here. At this moment, this axis is time. This is time. So the pulse shapes are plotted over time. But in this case, we plotted harmonic frequency component. The unit is Hertz. This is frequency axis. This one is a DC, zero frequency, and this one is the first harmonic frequency, and there is no second harmonic frequency, and the third harmonic frequency are this much. There is no fourth harmonic, fifth harmonic component this much. Sixth harmonic, there is nothing, and seventh harmonic, eighth harmonic is 0, ninth harmonic up to here. You can do all the way down. Then this graph shows some information. This rectangular pulse contains DC component this much, the first harmonic component is this much. There is no second harmonic, but third harmonic this much, no fourth harmonic, fifth harmonic. It means this graph shows the spectrum, means that if you plot, you can plot the same graph in these patterns. This is called the spectrum. It shows that the frequency component of the rectangular pulse. The same graph can be plotted like that. That is plotting over time. But the same graph can be transformed in the frequency domain. In the frequency domain, it says that this rectangular pulse contains these kind of harmonic frequencies. Okay, so Fourier series shows us that some signal has it's a harmonic component. How they are distributed. It means that as n harmonic index are increasing, the harmonic component are decreasing that way. Okay, as we know that it's n pi is magnitude of that one, so it decreases in that patterns. It has only other harmonic component. There is no even harmonic component. So we can see that what kind of harmonic frequencies are included in these patterns that can be found by the Fourier series. That is one of the important factor that we have to know from this Fourier series.